Good morning, students. In the last class, we discussed about the refraction from tensor medium to radar medium and also diffraction in prism, that is thin prism, convex mirror, and also that is concave mirror, and also through the lenses. Due to some technical problem, that video has been deleted. So once again, I am recalling that one, that is diffraction of a plane surface. So refraction. So in the last class we discussed that is the refraction that takes place from denser medium, that is from the radar medium to the denser medium. So here the refraction that takes place from radar medium to the denser medium. So if we consider this one is the surface, right? So surface is differentiated by the two mediums. One is medium 1 and another one is medium 2. So here medium 1 is considered as denser medium. So here the velocity is v1 and the second medium is considered as radar medium, that is medium 2 is taken as the radar medium. Here the velocity we are going to take on, that is v2. So as the wavefront travels from denser medium to the radar medium, so here the velocity v1 is less compared to that of the velocity v2. So the condition is v1 is less than v2. That is velocity in the denser medium is less and velocity in the radar medium is more. So considering one wavefront, so AB is the wavefront. So if the wavefront strikes the surface, in that the point A first strikes the surface A, makes angle into the surface, that is angle of incidence. Next, the time taken by the B point to strike the surface is time t. Then the distance traveled by the source B, that is the point B, each and every point on the wavefront acts as a source for the secondary wavelength. From this point, the distance traveled we have to calculate, we make the sphere of radius V1 into T. So that is the distance traveled, that is equals to V1 T. So if we make the sphere of radius V1 T, so if we draw the normal, so this becomes C, right? This is the tangent which is drawn from the A. So here AB is the incident wavefront. Incident wavefront. Next, we have to find the time t. The source B takes the time t to reach the point C. In the same time, the point A also travels, that is transmitted into the second medium, but its velocity is v2. That is, the source A velocity is v2 because it travels into the rarer medium. Then the distance traveled is v2 t. So here v2 is greater than v1 here, right? So then distance traveled by the source A, that is equals to v2 t. So in the same time t for both the mediums, that is for both the points to travel, then the distance traveled we can find by, that is the wavefront which we drawn by using the radius v2 t. So this becomes the sphere. Then if we draw the tangent from the sphere to the point C, then this gives the angle of refraction, that is R. So here if I draw perpendicular, then this becomes D, right? So this is the V2T, right? So if we observe this diagram, here angle of incidence is less than the angle of refraction. I is less than R because here the wavefront in the denser medium speeds, that is speed of the wavefront is v1, that is less than to that of the speed. Hence it covers smaller distance. Here it travels the larger distance in the same time t. So CD gives the refracted wavefront. CD gives the refracted wavefront. So this is the refraction that takes place when the wavefront travels from denser medium to the rarer medium. So as in the previous class we discussed, we derived the relation sin I by sin r. That is, we proved the Snell's law by using refraction of a plane wavefront. That is sin I by sin r, that is equals to n2 divided by n1. If the angle of refraction, this angle of refraction is 90 degree, then r is equals to 90 degree, then the value of sin r becomes 1. In that case, angle I is equals to angle IC, that is the critical angle. Then we can write sin IC, that is equals to n2 by n1. If the angle of incidence is greater than the critical angle, then there is no refracted wavefront. If the angle of incidence is greater than critical angle, then there is no refracted wavefront. That is, it transmitted the wavefront which it is refracted is no refracted wavefront. That is, it reflects back to the same medium. So that condition we call as total internal reflection. Total internal reflection. Right? So if the angle of incidence is greater than the critical angle, then there is no refracted wavefront. That is, the wavefront which transmit is into the second medium will be not there. It reflects back to the same medium, then that one we call as total internal reflection. In detail we studied this one in the ray optics. So here just briefly we are discussing the total internal reflection. The condition is the I is greater than IC. So this is about the refraction of a plane wave in rarer medium and in denser medium. Right? Similar, the refraction that takes place through a thin prism and a lens, that is convex lens, and also concave mirror. It is refraction of a plane wave. In that first one we are going to discuss is prism. That is thin prism. So if I draw, this is the thin prism A, B, C. Here BC is the base. Then considering one wavefront, incident wavefront. Like this one is the incident wavefront. On this incident wavefront, we have number of points. These points act as a source for the secondary disturbances. This is from the Heidel's principle. Each point, but here I am considering the 2 points. The arrow marks represent what? The direction of motion of the wavefront. That is, it travels from left to the right. So this one is the incident wavefront. So this one is the incident wavefront. As the incident wavefront falls onto the prism, here the lower part of the wavefront covers the largest distance. That is, it has to travel longer distance inside the prism. So here the prism is made up of the glass. Then it acts as the denser medium. Then here its velocity is less compared to that of the rarer medium. Here its velocity is less. Here we have 2 conditions. One is in the prism, as the refracted wavefront travels, that is incident wavefront travels into the prism, here the lower part of the incident wavefront travels longer distance, and inside prism velocity is less. So due to these two reasons, that is inside the prism, that is the prism acts as a denser medium. Here the velocity is less compared to that of the rarer medium. As the wavefront travel into the prism, the lower part has to cover the largest distance, and also it travels with the low speed, that is compared to that of the rarer medium. Hence, the refracted wavefront will be tilted like this. So this gives the refracted wavefront. Right? So this is what happens when the wavefront travels into the prism. Right? So the two reasons are why tilting of the wavefront, because of two reasons. The lower part of the wavefront has to travel the larger distance at the bottom of the prism. So if we consider here, if you observe this one as a larger distance compared at the top. And the second reason is inside the prism the velocity is less. Hence it has to travel more in the denser medium. Hence the refracted wavefront is tilted. So this what happens when the incident wavefront travels through the prism. The refracted wavefront we get is in the tilted position, right? So next, the wavefront which incident on the convex lens. So if we consider one convex lens, so this one is the convex lens. Then here we are considering one wavefront, that is incident wavefront. Here also considering 2 points. This one is the incident wavefront. Right. So this incident wavefront passes through the convex lens. Here in the middle of the lens, it has to travel the largest distance. Right. Here also the same case, but in the middle, it has to travel the larger distance compared to that of the edges. Hence, the refracted ray will be depressed. The refracted ray like this and converges to the point F, that is to the focus. Right, so somewhere here it is F. The refracted wavefront we get is, this one is the refracted wavefront. So here the refracted wavefront is spherical. In case of prism, we get the plane wavefront as the refracted, but in case of the convex lens, we get the refracted wavefront as spherical wavefront. Right? So these two converges at the point F. If the convex lens has a radius of curvature R, then the mean at the point F, that is radius of the sphere, is F. So this is about the refracted wavefront in case of the convex lens. So in case of convex lens, we get the spherical wavefront when the incident wavefront is plane wavefront. So next is concave mirror. So this one is the concave mirror. Right. So here also we considering one wavefront, that is plane wavefront. Incident wavefront. So after get incident on the concave mirror, we get the refracted refracted wavefront as spherical wavefront. So here also we get the spherical wavefront and they converges at the point F. Here it is F. If the radius of the concave mirror is R, then the radius of the sphere is F. So this one is the refracted wavefront. So this one is the refracted wavefront. It is also in spherical shape. Right? So this is how when a plane wavefront incident onto the prism, convex lens and also concave mirror, we get the refracted waves. In case of the plane prism, we get the plane wavefront as a refracted wavefront, and in case of convex lens and concave mirror, we get spherical wavefront, and they converges at the point F, that is at the focus. So similar way we can find for the concave lens and also for the convex mirror. But in our syllabus they mentioned the thin prism, convex lens and also concave mirror. So this is about the refraction of a plane wave and also the reflection of a plane wave by using the Huygens principle. So next, move on to the next topic, that is Doppler effect. So already we studied the Doppler effect in the class 11, that is in the case of sound. But here we are going to study the Doppler effect in case of the light. So what the Doppler effect says, the statement of the Doppler effect. So whenever there is a relative motion between the source of the light and to the observer, then frequency and wavelength may appears to change. So this phenomenon we call as Doppler effect. That is, it appears to change its frequency and also the wavelength. So that effect we call as Doppler effect. So what is Doppler effect? Whenever there is a relative motion, between source of light and observer, whenever there is a relative motion between the source of light and observer, frequency and wavelength appears to change. So this effect is called as Doppler effect. So here the main points are, that is the relative motion, that is the motion between the observer and the source of light. Either one may be stationary or both are moving. That one we call as relative motion between the source of light and to the observer. Here what happens means the frequency and wavelength. The frequency and wavelength appears to change. Actually not change, for appears to change. Actually the values are not changing. It may appears like to change. So this effect we call as Doppler effect. So if we consider one case, so here is the observer. Right, here is the observer, it is stationary observer as the source of light. So if we consider this one is source of light, from the source of light we are getting the wavefronts in all directions. That is waves or wavefronts which travel in all directions. As the source of light moves away from the observer or it moves towards the observer, what happens? So here considering as the source of light moving away from the observer with the speed v. So here is the stationary observer and the source of light is moving away from the observer. Then the wavefronts that are produced by the source of light. So if you consider these are the wavefronts, right? So these wavefronts has to travel larger distance, has to so the wavefront has to travel larger distance. Imagine here this one is moving. So if you consider somewhere here it is the source is moving, then the wavefront has to travel from here. So hence the wavefront has to travel the larger distance. So hence it takes larger time, right? So the wavefronts which are traveling to the observer, as the source is moving away from the observer, the wavefront has to travel the larger distance. Due to traveling of the larger distance, it has to take larger time. Hence, for the observer, the successive wavefronts which are reaching to the observer has to take a larger time as compared to that of to the source. So here the successive wavefronts which are producing, that is in 1 second, then it when it reaches to the observer, here the successive difference between the two wavefronts it may be greater than 1 second. Hence the wavelength or frequency which are measured by the source, then the frequency decreases due to taking the larger time for the successive wavefront at the observer as they measured from the source, then the frequency measured is decreased. So actual frequency, if we consider as true frequency, right? So this is the true frequency at which the source is producing, or the wave fronts emanating into the frequency, that one we call as true frequency as observed from the source. When it reaches to the observer, then here the frequency appears to decrease. So that frequency we call as apparent frequency. So here the frequency decreasing means the apparent frequency is less than that of the true frequency. That is, which is measured by the source. From the source, the wavefronts producing of the successive wavefront is, if for example 1 second, then when the wavefront reaches the observer, it takes more than 1 second. That is, time has large. Due to this time, the frequency decreases. If we measure from the source, then here the frequency appears to decrease. That frequency we call as apparent frequency. So apparent frequency is less than that of the true frequency. So if we write same in case of wavelength, means the frequency is proportional to inversely proportional to the wavelength. If the apparent frequency is decreasing, then the apparent wavelength is greater than that of the true wavelength, right? The apparent wavelength is greater than that of the true wavelength. Hence, the measured wavelength shifts to the red end of the spectrum. Hence, that one we call as red shift. The measured wavelength is greater than that is apparent wavelength is greater than the true wavelength. Hence the measured wavelength shifts to the red color of the spectrum. Then that shift we call as red shift, right? The condition ends as the source moving away from the observer. As the source moving away from the observer, the measured frequency is less than that of the true frequency. And if you write in case of wavelength means the measured wavelength is greater than that of the true wavelength. Hence, the measured wavelength is shifts towards the red end of the spectrum. Then that shift we call as red shift. So the condition is, the case is when the source is moving away from the observer, it has to, the wavefront has to take larger time to reach the observer, and also it takes larger time. Hence the successive, the difference in the successive wavefronts to reach the observer is more, that is time taken to reach the observer is more. Hence the frequency measured is less compared to that of the true frequency. Hence, the apparent frequency is less than the true frequency, and in case if we write in terms of wavelength, then apparent wavelength is greater than the true wavelength. Hence, measured wavelength is shifts towards the red end of the spectrum. So, if we consider, so this one is the spectrum. Here it is red, and here it is violet, indigo, blue, green, like this. Hence the measured wavelength is shifts towards the red color. Hence that shift we call as red shift. That is for the source moving away from the observer. Next, if the source is moving towards the observer, if we consider here, right here is the source. The source is moving towards the observer. So here is the observer, the source is moving towards the observer, then the wavefront takes smaller time to reach the observer. Hence here the measured frequency is greater than that of the true frequency. So the condition is source is moving towards the observer. Source is moving towards the observer, then here the apparent frequency is greater than the true frequency. If we write in case the apparent wavelength is less than the true wavelength, hence the measured wavelength shifts to the blue color, that is blue end of the spectrum. Hence this one we call as blue shift. So this one we call as blue shift. So here we are considering the two cases only, that is for the stationary observer the case one is moving away from the source is moving away from the observer, and in case 2 the source is moving towards the observer. So the source is moving towards the observer means the apparent frequency is greater than that of the true frequency. If you write in case of wavelength, the apparent wavelength is greater than that of the true wavelength. Hence the measured wavelength is shifts towards the blue end of the spectrum. Hence the shift we call as blue shift. So this is about the Doppler effect. So in the Doppler effect we studied so red shift and also the blue shift. So this is in case of the no medium. If there is no medium, if we consider the observer and the source, that is there is no medium, that is in vacuum, the source of light moves away from the observer, then we get the red shift, and the source of light moves towards the observer, then we get the red shift. Right? So this is about the Doppler effect. Next, so if we write the formula for the Doppler effect, so net fractional change in frequency delta nu divided by nu, that is frequency is denoted by nu or f. So here if I write f or nu represents what? Frequency, or delta f divided by f, where f is the frequency. So net fractional change in the frequency, that is equals to minus b radial divided by c. So this is the formula. So this formula is valid only when the speed of source is less than to the speed of light. Speed of source is less than to the speed of light. That is, speed of light is denoted by letter c. So here v radial represents what? The radial, that is the component of. So v radial means the component of speed of the source, the component of speed of source between the line joining, between the line joining source and observer relative to. So this one is the V radial. So it is the component of the speed of the source between the line joining source and the, that is straight line joining the source and observer, that is related to that of the source. That is the net fractional change in the frequency delta f by f, that is equals to minus v radial divided by c. That is, speed of source is less than c. For this condition, we can use the formula delta f by f is equals to minus v radial by c. So this is the formula for the Doppler effect. So remaining cases, we can use the formula which we previously used, that is in the in the speed of sound. The formulas which are using in the Doppler effect, the same formulas can be used here only. So the main is the Doppler effect. The main one is the red shift and also the blue shift. For 1 mark, they may ask the question, so what is red shift and what is blue shift? So what happens when the relative motion between the source of light and observer, the frequency and wavelength appears to change. This appears to change is the apparent frequency and apparent wavelength. The actual frequency and actual wavelength we call as true frequency and true wavelength. So this is about the Doppler effect. So one application of the Doppler effect is, that is, we can measure the relative approach of stars and galaxies, that is, they are approaching or receding from us. So that one is the application of the Doppler effect. So the application of the Doppler effect is, we can find the stars and galaxies which are approaching to us or they are receding from us. So that one is the application of the Doppler effect. So this is about the Doppler effect and redshift and also the blue shift. For 1 mark, they may ask what is redshift and blue shift. And if they ask the application, means to find the stars and galaxies which are approaching to us or which are away from us, that is, they are receding from us. So in the redshift means the stars are receding from us. Right. So next topic is interference. So this is the phenomenon. So what is interference and the what happens in the interference by using the principle of superposition. We are going to discuss the interference. So in the next class we can discuss the topic interference, and in the interference we have further constructive interference and destructive interference. Then we study the interference in case of phase difference and also in case of path difference. That is, the theory of the interference is very important. They may ask for 5 marks. For 5 marks, they may ask give the theory of the interference. Then interference we have two interference. One is constructive interference and destructive interference. And in this we have Young's double slit experiment. That one also very important. And next, what is coherent source and incoherent source, and the intensity of the coherent and incoherent source. That is, the interference is the redistribution of two or more light waves which superimpose. So that phenomenon we call as interference. So what is interference means? The light redistribution, that is distribution of light when two or more light waves superpose on each other. Superpose means overlap on one another. So one light falls, that is one wave is falls onto the another wave. So that phenomenon we call as interference. So in the next class we will detailedly discuss the topic interference. Thank you.